So we were discussing about the third harmonic magnetizing current and its necessity in a transformer to make the flux sinusoidal in the core. Just to highlight the points we discussed last time, you should remember that to obtain sinusoidal fundamental frequency of flux in the core of the transformer, to obtain sinusoidal induced voltage, the flux must be sinusoidal of one frequency f. The second point is to have sinusoidal flux of frequency f. The magnetizing current of frequency f will not do. You would require, in addition to that fundamental frequency magnetizing current, a third harmonic component of current to be present, such that the flux will be sinusoidal. And the third point to note is that in a three-phase, three-wire system, no third harmonic current exists. It is not possible. So, in the light of these 3 points, let us continue our discussion with star-star transformer and see what happens. See, this also we discussed briefly. I will just tell you quickly. Suppose if you have got a star-star connected transformer with neutral not present, only the 3 lines are present, A, B, C, and you apply 3-phase balanced supply here, 3-phase supply balanced. Then the magnetizing current which will be drawn from the supply cannot contain a third harmonic component. So it will always draw a current of fundamental frequency omega, which is equal to 2 pi f. So here current is known, therefore by referring, just I will tell quickly this one. So I know now the current distribution. Current distribution is known like this. This is the current. This is I, and in this one, this is I. You remember, this is I or H, and this axis is B or phi. Then current is sinusoidal or fundamental frequency f. But if you go back here, the flux distribution will not be sinusoidal because it is a double valued function in this hysteresis loop, and the nature of the flux distribution will be flat topped, which will make the induced voltage in the various windings distorted. It will contain, induced voltage will contain fundamental frequency and a third harmonic frequency, and it will put additional stress on the insulation of the transformer. Now, in order to avoid that problem, one solution could be that suppose if the neutral is available, this neutral you connect here. If you connect the neutral, then the third harmonic current can exist. Applied voltage across each winding is sinusoidal. Flux has to be sinusoidal. If flux is sinusoidal, then I will go this way to obtain the nature of the current, which will contain third harmonic. And third harmonic current can now flow through this returned neutral wire, and it will make flux sinusoidal, and you will get induced voltage in both windings and lines sinusoidal. Remember, in the earlier case, when this neutral were not connected, then the phase voltage, although it would have contained a third harmonic voltage, but line to line, the voltage would have been purely sinusoidal of fundamental frequency. But to avoid this problem in this fashion, this is one way of doing it, no doubt. The third harmonic current will flow via this neutral wire. But the frequency of this third harmonic current will be about 150 Hertz, is not? And this may interfere with your communication wires, which may run side by side with your power lines, is not? Transmission lines, along that only the communication lines are also laid, telephone lines, like that. Therefore, this high frequency means this 150 Hertz component of current may interfere with your communication network. Therefore, this is not commonly used to make flux sinusoidal in the core in order to get sinusoidal induced voltage between the lines or across the winding. Another way of doing it is in this fashion. This you just try to understand. Consider a star delta connected transformer. With neutral not connected, and that is the connection will be like this. The primary is star. Of course, these terminals will not show. It is understood we have correctly connected it in star, and this is suppose this side is delta. And suppose this delta, before completing, I have put a switch here. A switch. Which if I close it here, it will complete the delta. Let us understand what will happen. Suppose this primary side, which is connected in star, is supplied from a supply frequency of 50 Hertz, that is F. 50 Hertz. Tell me, under this condition, what will be the nature of the flux in the core of the transformer? Will it be sinusoidal? It will be flat topped. That is, the flux distribution in the core will have a fundamental component. Flux in the core will have frequency F and 3F. Naturally, this F and 3F frequency fluxes will induce their own voltages in all the windings. Okay. Now suppose I take a voltmeter and connect it between these 2 points of the series connected secondary, which I want to make it delta. Afterwards I will do that. But comment on the voltmeter reading here. How much the voltmeter will show? It will be of the third harmonic voltage, it will read. Why? Because the fundamental frequency voltages will be induced, VA, VB, VC. And of course, this series connection I have done correctly with due regard to proper polarity. And suppose let us assume only fundamental frequency exists. Then what is this voltage? This is 0. Sum of all the balanced three-phase voltage will amount to 0. But the third harmonic voltages, which will be induced in each of the windings of frequency 3F, what is the phase displacement between them? 0. They are co-phasal voltages. Therefore, the voltage here you will be getting 3 times the induced voltage, third harmonic induced voltage here. This will read 3 times the induced voltage, third harmonic, in each winding, per winding. This voltage will be induced. Okay. Therefore, in a start, primary side start, secondary side delta, each winding will have fundamental frequency, third harmonic frequency. But the sum of all the fundamental frequency voltages will be 0. But third harmonic voltages will be co-phasal in nature. Therefore, their algebraic sum, it amounts to that. 3 times of that will come across the voltmeter. Now, we find that in this circuit, there exists a third harmonic voltage. Now, if this switch is closed, what is going to happen? This third harmonic voltage, which is induced here in the windings, each of the winding, will now circulate a current here. The magnitude of the current, of course, will be decided by the third harmonic impedance of these windings. But some third harmonic circulating current will flow. This third harmonic current, after you have completed the delta by closing that switch, can there exist any third harmonic current here in these lines? Not possible. In a 3-phase 3-wire system, no third harmonic current can exist. So this current will only circulate here. There will be nothing reflected in the lines here. Now what happens is this, in this particular type of connection where delta connection is present, the transformer can produce its own third harmonic current requirement. See, this current, third harmonic current, will have no component reflected on the primary side, because here no third harmonic current can be present on this line, because neutral I have not connected. Therefore, what happens is this: the magnetizing current will now consist of this fundamental frequency, whatever is drawn from this supply, and the much needed third harmonic current the transformer develops by itself, and trying to make the flux more sinusoidal. Therefore, delta winding transformer, whether this neutral is connected or not, it tries to make the flux sinusoidal on its own. You need not worry about it. Unlike in a star-star transformer with neutral not connected, here no third harmonic magnetizing current can flow. It cannot exist in the lines. It is as simple as that. However, in a connection where delta circuit will be there, the transformer by a self mechanism will try to circulate a third harmonic current and therefore try to make the flux sinusoidal in the core of the transformer, thereby solving somewhat the problem of non-sinusoidal voltage between the lines. So sometimes what is done is this, that in a star-star connected transformer, which is to be used as star-star connected out of some compulsion, that is the level of voltage of the primary and secondary both are high and you have to use star-star connected transformer. Then in that transformer there will be additional windings provided on the secondary side which will be kept connected in delta fashion, and such a winding is called tertiary or stabilizing winding. That is, for each primary there will be two secondaries. One set of secondaries will be connected in delta. This is, secondary. This is secondary. This is also secondary. Like our three-phase transformer connection. Suppose you have a transformer like this. Primary one winding, two windings. So one set you connect in delta. Other you connect in star. In that case, that third harmonic current, magnetizing current, will be circulating in this delta, and it will try to make the flux sinusoidal in the core, and thereby making the voltage in the windings and the, of course, lines. It is already ensured the voltage nature will be more or less sinusoidal. So such windings which are provided, additional windings, are called tertiary winding. Why it is also called stabilizing winding, I will tell you. But you remember that a transformer having both secondary winding and tertiary winding, which is called like this, you can supply load from both the secondaries. Sometimes, if it is needed, that you can have different two voltage levels on the secondary side, different number of turns. You can also supply tertiary winding, can be used to supply also additional load if needed, like that. Now, another problem with star-star transformer that I must tell is the oscillating neutral. In star-star transformer. What I mean to say, that suppose you have got a transformer which is connected in star-star fashion and neutral not connected. That is, this is the common point of the transformer O, and primary is energized, and this is suppose the supply voltage terminals ABC. Now, as told earlier, since the magnetizing current here will have only fundamental component of current, therefore flux in the core will contain a third harmonic component, and the induced voltage in each of the winding will contain a fundamental and third harmonic. In each winding, fundamental and third harmonic. Now, therefore, in any phase voltage, suppose that is each winding the phase voltages. If I draw the phasor diagram, suppose this is A phase voltages because of fundamental frequency. This is A, this is B, this is C. This plus and this phasor rotates at a frequency of F or omega. Plus another third harmonic voltages will be there in each of the windings, and these voltages will be in phase of equal magnitudes. Suppose in the windings, what are the voltage phasors present? This fundamental component frequency and third harmonic voltages. And third harmonic voltages are co-phasor, so I have shown it like this. But they will rotate at what frequency? 3f. In the phasor diagram, you do like this. Now, in a power system, when a transformer, these terminals are connected to these voltages, you know that this is called, I told you in the earlier lectures, that our power system is a grid connected system where several generating stations will be connected in parallel, and it is called what it is called? Such a bus, right? It is called a bus, three-phase bus system, where the voltages are fixed. Voltage and frequency you cannot alter by doing something, by connecting another small machines like that. You cannot alter because it gets fixed by so many big generators connected in the system. So what happens? These voltages A, B, C points, these are fixed here. Supply voltage which is connected to a three-phase bus, these phasors will be fixed. Now what happens is this is interesting to note why the neutral oscillates. Suppose you consider this is your A phase voltage. A phase, this is your B phase, and this is your C phase voltage. And as you can see, to draw a phasor diagram on a plane, all the phasors should be of same frequency. Then only you can represent them relatively this one. Now, how these phasors can be summed up with this? You consider it to be stationary and this to be moving with a relative speed of twice f. Okay, this way one can represent. Now, this let us assume a instant when this zero third harmonic voltages will be like this. All the three voltages will be in this fashion. Suppose let us call this, I call at omega t equal to 0. I am counting time when this phasor, which moves with a frequency of 3f or relatively at a frequency of twice f with respect to this, and this I will show at f. So what will happen? With time, this will go on sweep past all the three phases. So at this instant, suppose they coincide with this a phase. Suppose at omega t equal to 30 degree, what will happen? A phase will move by an angle of 30 degree like this. And B phase will suppose come here after say 30 degree, and C phase will be there. At that time, where this will be? Where should I draw? This third harmonic voltage? Right, 90 degree horizontal. It will be like this. So, at this point of time, at omega t equal to 0, this will be actually your A phase voltage, because sum of these two voltages is your this one. B phase voltage will be this one. That is this voltage plus this voltage will be this, if you draw this parallelogram. And C phase voltage will be this one. So, magnitude of the voltage with respect to that common point will go on changing with time. And that is, and at this point, this neutral point will be somewhat like this. This one will be A phase, this one will be B phase, and this one will be C phase. So in this way, you can draw it at various instants. The point to be made here is that the neutral, or I should not say neutral, this point O will be having different potential with respect to A, B or C at different instant of time. So this point is not fixed, it oscillates with time. This problem too will be solved if you provide a tertiary winding, because the cause of this problem is, of course, these third harmonic voltages which are present. So this, if you can somehow nullify, this effect too will be not present. So that is why it is sometimes also called stabilizing winding, which may be present in a transformer, and it will be definitely present in a transformer which you want to connect it in start-start fashion. So a delta connected winding can be provided extra, which is sometimes called a stabilizing winding or a tertiary winding, to suppress the third harmonic flux, hence to avoid the third harmonic voltage in the line. Anyway, you just go through once again M.G. Say's book. M.G. Say's book to know further. Now, what I would like to tell, that a delta connected transformer therefore will be a better choice. Another problem I will just tell, just in qualitative term, of a star-star connected transformer is single phase loading. This I will just highlight. What is the problem? Single phase loading of a star-star connected transformer. Suppose you have got 3 single phase transformers connected in star-star fashion. First I will tell you the observation, then I will try to explain physically what happens. Suppose forget about that third harmonic voltage, okay, let there be some third harmonic voltage induced, like that. It is star-star connected, neutral not connected to the source neutral. 3-phase, 3-wire system on both the sides. Okay, you have connected suppose an ammeter and a switch and a load. And this load you have connected to this common point, in order that you want to supply a single phase load from this 3-phase transformer. Very practical thing one can do in the lab, no problem. Now what you will observe is that if you energize this 3-phase supply, you give, here we will find induced voltage in all the windings, line to line balanced voltage is there. Now what you will observe, if you now close the switch and start loading the transformer, that is go on reducing the impedance of the load. To load it means you have to reduce the impedance connected. What do you think your ammeter will read? One way to explain it, why it will read this much, this per phase voltage divided by this impedance magnitude, this much it should read. But you will observe the ammeter is not showing much reading as expected. You further load it, you will find ammeter is still not showing. I mean, you go on loading means you are think in terms of a loading rheostat. You are going on reducing the resistance. And as if you go to the extent of very low resistance, till you find ammeter does not read. Now, why such a thing will occur? It will occur because of this fact. Suppose this is A phase. This is suppose A1, A2. This is suppose B1, B2. This is suppose C1, C2. And here it is suppose A1, A2. B1, B2 connected correctly, C1, C2. Okay, now suppose you have start from the first point, there were ES voltage existing in all the windings, you load the transformer and let us assume okay some current will flow in this transformer. The moment current flows here, there will be reflected current in the corresponding phase in order to keep its flux constant, is not? Suppose 3 different transformers you have taken. The flux like this, 3 transformers are there. Now the point is, if you load the secondary of a phase, there must be additional current drawn from a phase here in order to keep the flux in its core constant, MMF balance. Suppose it draws that current it draws. Some IA current flows here, it draws additional current IA by its turns ratio, etc. But this current has to go back to complete its path on the primary side. How it can complete? There are 2 ways out. It will go like this and this, it will divide through the B and C lines. Okay. But through the B and C lines, if it flows, the secondary of which is not carrying any current, then the flux in these 2 transformers will upset. Is not? So what I find that on the secondary side, B phase, C phase are not loaded. The impedance here offered will be what? What impedance it will see? Only the magnetizing impedance of this winding and of this winding. Because here nothing is connected. In a transformer, what is the impedance? You draw like this. Per phase if you draw. This is Rx. For B and C phase transformer, nothing is connected here. So, what is the equivalent circuit here? Only this branch between this point and this point, high impedance. Similarly, for this high impedance path is there. So, what happens? Current really cannot flow for this high impedance. But then, who satisfies this Ohm's law here on the secondary side? I mean, Ohm's law means voltage I have applied. There is some impedance. Actually, what happens is this, to satisfy this one, on the secondary side, it happens like this. This neutral point, this O point, as you go on loading, will come closer to here. That is, more voltage will be induced in the B and C phases. Because that current, whatever little will flow, will produce extra MMF and produce larger voltage here. So the neutral drastically shift towards phase A, making the voltage here is very small. And therefore there will be neutral shift. So this will be another problem. And one can go to the extent of loading to a very high degree of loading, means going to the extent of short circuiting. Of course, in short circuiting means what? This voltage will be how much? 0. So this voltage goes on reducing. But should this be allowed? Suppose, okay, some current is not flowing, but should I allow this thing to happen? What happens to the voltage impressed across other winding? That approaches to the line-to-line voltage. Okay. So single phase loading sometimes become problem, particularly with transformers having different magnetic circuits. I will just make up to this comment is in the machine to some detailed analysis I will do in my next machine class. But you remember that star-star connection, simple star-star connection with neutral isolated, not connected to the source neutral, gives rise to several problems sometimes. And one of the problem is oscillating neutral. Single phase loading sometimes become difficult, particularly with separate single phase transformers and uncoupled magnetic circuit. And then you can solve this, of course, by connecting this neutral, this point. If you connect to the supply neutral, these problems will be solved But in that case, this neutral wire will carry that third harmonic current and may interfere with communication network. And once this happens, of course, that loading problem will not be there, this neutral if you connect. So this way it can be done. And lastly, I will tell you these problems, of course, will not be there in zigzag connected transformer. Why it is done can be understood from our previous diagram you can refer to. Suppose zigzag connected transformer, as I told you, it is basically a start-start transformer. Suppose this neutral I have not connected to the supply neutral. So these currents will be only fundamental frequency. So flux in the core of the transformer will contain a third harmonic component. The induced voltage in all the windings will contain F3F like that. Okay, fundamental, third harmonic. And third harmonic voltages will be cophasal. Okay. Tell me, between, suppose the secondary is Z1, this connected. If I connect between A1 and B1, do you expect any third harmonic voltage to be present on the secondary side? No, because these third harmonic voltages are cophasal. If you mark proper polarity, this voltage will cancel out between line to line. Between one line and its common point, will there be a third harmonic voltage? That is, I will connect a voltmeter between these 2 points. These 2 points. Yes. In start-start transformer, it will be yes, correct. But here, why it will not be? Can anyone tell me? This will contain third harmonic voltage. This will contain third harmonic voltage. The polarity is okay, yes, they are opposite. But you see the connection, A2 is connected with what? C4. See, A1 terminal with this A1, third harmonic voltage I will only draw. Suppose at any time A1 is positive, A1, and this is A2. This is third harmonic voltage, with this plus, this minus. Now, what is the other winding in connected? C4, C3. C4, C3. So this will be also their cophasal. Which one will be plus, minus? C3 is plus and this is minus. And this is plus, minus. So these are connected. So resultant third harmonic voltage available between these two will cancel off. It will be 0. So what I mean to say, it is at least slightly better than star connected transformer, start-start, simple start-start without neutral. If you compare with star zigzag without neutral, it is better. Both the phase voltage will be sinusoidal, line to line voltage will be sinusoidal. That is, you can supply a single phase load. Now similarly, you tell me, in this case, if I want to load the transformer by a single phase load, will there be problem? Can I load that one without the problem faced in the earlier case, because B, C phase were open? In this case it will not be so. Because of what? Suppose you have connected a load between A and this common point and some current let it drive. You find that there is a phase mixing between the common point and one of the terminals here. See, A phase and C phase on the secondary side, both of them will carry current, supply that load current. Getting or not? This current will have their reflected part in both A and C phase. So there will be a return path from A to C phase. You getting? So if you connect a single phase load between one line and the common point of the secondary of zigzag connected transformer, what I am trying to tell, that single phase loading is possible, no problem, no neutral shift will occur. Why? Because this A phase will carry current, secondary side. C phase will carry current, and both of them will have their own reflected currents on the primary A and C, and it will complete its path. And if you look at the direction of the currents also, it will nicely match because of the polarity reversals of series connection. A2 is connected with A4. This you verify. This third harmonic single phase loading is also possible. Now I will these are some things I told without doing practically any mathematics, except that I told that from physical consideration that there will be some third harmonic current must be there in order to make flux sinusoidal, things like that. No extra mathematics I did to do that, and tried to highlight the problems. Therefore, remember that there are several connections now available in a transformer, of which star-star connections when to use. I will just briefly tell star-star connection when to use. Generally, it is to be used for relatively high voltage ratings on both the sides. High voltages, but less currents, less currents. Then you have, say, delta connected transformer, generally to be employed for relatively low voltages. And maybe high currents, because currents in the windings will be √3 times less. When I say about currents, I mean the line currents. Line currents. So high currents. And the other combination, of course, will follow naturally. That is, when primary is high voltage, primary high, secondary low voltage, and so on, delta star connected transformer, like that. Of which, of course, the star-star connections may give you some problems, unless it is provided with a stabilizing delta connected transformer, delta connected additional winding on this transformer. Delta connected transformer has got its own advantages. Tell me something. One thing is clear, the third harmonic business we need not bother, because third harmonic voltages, whatever will be induced in the winding, that will try to, in a self way, it will try to make the flux more or less sinusoidal. So that problem will not be there. What other advantages? One open delta connected thing you can do. Of course, provided these three transformers are separate single phase transformers used. It is, of course, if it is a three-phase transformers as a whole, one does not do that, because other winding should be replaced. Then start delta transformer, whether neutral is connected or not, once again is devoid of that problem. Third harmonic problem will not be there, and delta star like that. Zigzag connected transformers are costlier. In the sense, you have to put additional turns on the secondary. This point one can easily understand. Suppose when you compare two things, compare with same voltage. Suppose the voltage rating is suppose some 6600 stroke say 1000 volt. You just try to compare. Same flux level in the transformer. I am asking you a question. Suppose I want to have three-phase line-to-line 6600 volt. On the secondary, I want to have three-phase 1000 volt line-to-line. Okay. You can do it by a star-star transformer or a star-zigzag transformer. Okay. Comment on the number of turns necessary on the secondary sides. Same flux level I will be using. Have you got the question? No. Should I once? Not got. Suppose I want to transform, say 6000 volt, 3-phase supply, line to line. To I want to change it to 1000 volt, 3-phase, line to line. I want to get it. I have decided I will employ a star-star transformer, Y. And another option is star zigzag transformer. I will employ. Flux level in the core I will keep same. Flux level, because two things must be compared with this one. Flux level same. So primary turns of each phase, what do you think? They will be same or different? Same. Same number of turns here, N1. Here it is N. What I am asking you on the secondary side, it is a simple single winding secondary. The total number of turns, if you count in a particular phase, starting from one line to this common point, what is the total number of turns present? And in this case, starting from one of the phase to the common point, if you count the number of turns, will they be same? I am asking. No. In which case it will be more? Zigzag case. Because of the fact that these two voltages, yes, number of turns here, this plus this number of turns, and induced voltage per turn is same. However, these voltages are not added algebraically. They are shifted. Voltage available is less. Are you getting? Therefore, number of turns needed in fact, you can easily work it out. What is the number of extra turns one needs in such cases? So that point I wanted to tell. Zigzag is a costly transformer. Of course, it does not suffer from this one. Now, I will tell you about this thing, about phase transformation. That is, if you have a three-phase supply, can you get a six-phase supply with the use of transformers? Six-phase supply or 12-phase supply, like that, or a two-phase supply. Two-phase supply. Tell me where six-phase supply is used. Where, generally six-phase supply you will call for. I need a six-phase supply. You have read about rectifiers or converters? Rectifiers? Bridge rectifiers? Three-phase rectifiers. Three-phase supply you use. Now that voltage ripple, it can be made more a DC if you have six-phase supply. See, in a three-phase transformers, I will quickly tell. If you connect like this, you get a three-phase voltage, rectifiers, diode, let us. This is the load. What will be the ripple voltage? Like this, three-phase voltages will be there. Now, if you increase the number of phases in a rectifier converter circuit, then the voltage ripples will be like this. It will be more smooth a DC. There it is necessary sometimes to have six-phase supply voltage or 12-phase supply voltage. Now anyway, I will not digress to that. But suppose the problem is from a three-phase supply I want to get a six-phase supply. So how can you do it? So you now have a transformer which is having two identical secondaries, like your zigzag transformers. See, this I will quickly tell because nothing serious about it. So you have got two identical secondaries. I will not draw like this. Instead of connecting it in zigzag, what you will do? You connect, this is suppose primary connected star. This one you connect YY0 and this one YY6. So this way and this way you connect. And these two you short. So with respect to primary, you will get one set of voltage like this. And the other set of voltages will be like this. So YY0 plus YY6, I mean the other winding. These two will give you this way. And these angles will be 60 degree. And it is a 6-phase balance system you will be getting. Can you get a 6-phase balance supply by other 3-phase connections? This is, of course, some of you really come up. Okay, fine. What about other connections? Is it possible, whatever you have taught? Yes, you can get another connection, delta-delta connection. What you have to do is this, in this case, you connect these two sets of windings are there. How will you connect? You connect one set as DD0. Another, the primary is same for both this one, DD6. So that delta connection you do. Then the voltage phasors will be like this. With respect to your primary voltage. And the other one will be what? Like a star. These terminal markings I am not doing because we have done so many times. You will be able to do this DD0 and DD6. So these voltages available will be a 6-phase voltage, balanced. However, see, there is no interconnection. You remember, I mean, these two sets of secondaries, if you look at, I'll not draw with terminals. One will be connected like this, is not. Another will be connected with proper these terminal markings, this way. Now, these points I make some marking, whatever will come, say 1, 2, 3, 4, 5, 6. Suppose this is 1 here. Some 2 will come from this side. If I connect a voltmeter, will it read? How it will read? Between 1 and 2, if I connect a voltmeter, these are isolated. Is not? Balanced 6-phase voltages will be there, provided you connect a balanced 6-phase load. Then that return path will be available. Suppose this 6-phase balanced load, 6-phase load you connect, balanced. And these wires you join. From here 6 terminals will come out. Consider that 6 resistances are connected in star. 6 terminals will come out, one common terminal. So these 6 you connect here. 1, 2, 3, I mean like this, 4, 5, 6. 1, 2, 3, 4, 5, 6. So you complete this connection. Then these voltages will be available. Via that resistance, it will complete its path. Therefore, by connecting either in star-star fashion or in delta-delta fashion, DD0 and DD6, one can get 3-phase to 6-phase voltage. The last conversion, and similarly one can, by having several windings on the secondaries, one can have other connections as well. So tomorrow I will tell you about the 3-phase to 2-phase conversion. Thank you.